Does the cable reach the other end of the table? Because I don't want to try this. It could work with a bit late on the... Maybe, yeah. So that I don't... camera is... yeah. Okay. No, this was not the first slide. I'm sorry. Oh. Oof, oof, oof. How do I exit? Da, da, da. Yes. Okay. So, hello. Thank you for coming. As you already said, my name is Giovanni Gherdovich. I work at SUSE. And I am based in Prague, in Czech Republic, although I am originally from Italy. Some of the material that I'm going to cover is of introductory level, and so in order to be more effective, I'm going to read it from my notes, if you don't mind. That doesn't mean that you cannot. Feel free to stop me if something is unclear, wrong, okay? So as I work in the performance team at SUSE, didn't mention that, and as a performance analyst, I have a specific professional bias. First off, the team I work in is concerned about server workloads, so no mobile, but server. And regarding power management changes, we assume that the upstream author of the change has met their energy saving goal, and we consider our role to be that of making sure that the performance trade-off that has necessarily been done is acceptable. So we don't act for saving energy, but check. And we support all the major architectures, but our grid of machines reflects our customer base, and so is strongly skewed towards Intel x86. We have only one ARM box, servers from the vendor SoftIron in our performance regression testing loop, and yeah. How big? The large, they are, so the large machine, 80 cores, dual socket, and 500 gigabyte of RAM. This is the big machine we have, and we have 4 of that. One thing that we have is that we have a lot of redundancy. Like we have among those 15 machines, we have. Like if you remove duplicates, it's going to be 3 type of machine. So like we have 8 of the same, 4 of the same, and 2 of the same. That's very convenient for studying bugs. You know, you can run a bisection on one of them and then trace on the other one, so you can work in parallel. It's kind of practical. Not big like 1,000 core. No, we don't have that. Oh yeah, yeah. That's old. Okay. We have one 4 socket, but that's old. It's not. It's not. It's before Haswell. So. Yeah. No. Actually, yeah. The person who purchased the hardware, which is my manager Mel Gorman, he is quite attentive to like it does it. If it's something is used in our deployments, we try to get it. So it's we try to reflect what actually is the deployment. It's not like.
Socket customers are also the ones who pay us the most.
Okay.
So we like to listen to what they
Of course, that's what we do. Exactly. This is. So if we need, for example, to debug a problem on PowerPC or mainframe, we have to borrow the machine from another team, and so those machines are what we have as in our performance team. We are 8 people. It's not a big team, but yes, and those run a continuous loop of testing, and sometimes we take a machine out of the grid and we make an investigation if there is a need. So outline. In this presentation, I'm going to refresh your memory about a patch written by Peter Zelstra about and sent to LKML by Srinivas Pandruvada from Intel about 12 months ago. I'm sorry. And this patch represents a possible angle of attack to the problem of implementing as a frequency scale invariance on x86. The patch circumvented the issue of defining the max available frequency on an x86 system by assuming it to be the maximum turbo frequency, one core turbo. So we assume that that is always available. You can, so this was the simplification made in the patch. At the time it was proposed, a few people pointed out that this frequency may not be available to a core if other cores, neighboring cores, are not idle. Specifically, Yuri Lelli built a Lisa test case to recreate the exact scenario and posted a plot of the util-AVG signal of the root run queue over time. In that plot, the util-AVG signal couldn't reach its maximum value of 1024, despite the corresponding CPU being fully busy. The reason was, obviously, he wrote the test for this purpose, that another core in the same socket, yes?
So I wrote that patch assuming or building on Vincent's time scaling.
Yes.
And that never...
I'm very happy that you are saying that, because I knew that you were about to say this thing, because every time we mention that patch, you say, but this works with the Vincent patch.
Right.
Vincent patch is now in 5.2 RC1, and I had tested, did the homework on this. So, yeah, so I tested...
This looked like it was prepared before.
kind of predictable. No, I'm joking. So yeah, so there was this objection by Yuri, and that's it. So what I did and I'm going to present in this report is that I ran the benchmarks that I usually utilize to evaluate CPU frac changes, and those and the results that I got applying on top of 5.0, Vincent new invariance and one core turbo. I also tried one core turbo without Vincent, and I also tried all cores turbo with and without Vincent. I mean, just to see.
And did you then clip it to 1?
Yes.
Okay.
And the results are that all those 4 variation, like one core, all cores, with Vincent, without Vincent, they all perform very well in a specific situation, and almost embarrassingly well. When I saw the dashboard, I saw those gains, and I like, for example, 10% on an I/O benchmark called tbench, 15% on kernel compilation, and in what specific case? When the machine is lightly loaded. Example, my machine is 48 cores, so, and I run the kernel compilation benchmark, compile the kernel, parameterized over number of jobs. So I ran it with 1 job, 2, 4, 8, 16, 32, blah blah blah, and the results I get out of 4 jobs and 8 jobs are very, very boosted by this patch. The saturation case does not regress. So this is what I observed. I was very skeptical of this stuff. Like I saw this like in the last few weeks got these results, and I didn't want to. I want to make sure this was not something that I got out of luck or chance or random fluke. So I repeated them, changed something, repeated again. Now I'm fairly confident that it's kind of real, that there might be something, like it's not random, like it's not some mistake that I made. So this is the feeling. Repeated many times, the tests, and I think Intel Piste. Oh, no, wait, no. I only, so 5.0 with the schedule chill is my baseline, and no, I didn't type it. Yeah, with that obviously, yeah, because P states is a bit better than schedule chill at this point. I mean, not yet. Exactly, the best in class x86 frequency governor is not yet schedule chill. is enthalpy state with the power say with the governor enthalpy state power save. These are the name in the x86 word, and active mode. Yes. In this thing, I use the enthalpy state passive, so I use it as a driver, and I use schedule chill as a governor. So test results, lot of green. I'm not sure I understand this result yet. I have an hypothesis. Sorry. No. I'm just saying that I have an hypothesis, but I haven't traced, investigated why. So not sure I understand what's going on. I have an hypothesis, which is massive boosting opportunity are enabled. So machine is idle, only a few jobs. Those get a lot of turbo boost, and this is what I think is happening. So anyway, back to introductory material. Being a frequency scale invariance, it's a quality, a property of something. So you have something, and this something may or may not be frequency scale invariant. This something are the PELT signal, util AVG, and load AVG. Frequency invariance of PELT signals is implemented in software, in the kernel, and the ARM platform has had this property implemented for quite a while now. Let's consider util AVG. A task running at half the frequency takes twice the time to complete its work. But since util AVG is a function of its running time, a task running at half the frequency will also have a larger util AVG because the running time is larger. So what is the value of util AVG for our task? Is it small or large? Utilization is ill-defined. A task looks larger just because the machine is running slower. This known invariance makes so that util AVG of two tasks running on different CPUs at different frequencies is not comparable, nor is the util AVG of a given task comparable with the util AVG of another task, of the same task 5 seconds ago in the past, because the OPP has changed in the meantime. If we have some quantity Q, such as PELT contribution or time, since we want to make it frequency scale invariant, we multiply it by the ratio of current frequency and max frequency. In x86, this isn't trivial because we don't know the max value of the frequency that the frequency can achieve at a given point in time. The availability of turbo states depends on how much power the socket is consuming. If neighboring cores are quiet, we may have access to a turbo state. If they are busy, we may not. A variety of strategies have been proposed to address this issue. First one by Pelzelstra is to pretend that we always have access to the highest possible turbo state, the one where only one core is active and all others are idle. Less aggressive version of this is to assume that our max frequency is a slightly lower turbo level, such as the one where all the cores are active at the same time, which is a frequency value just a tiny bit higher than the so-called max P, which is the maximum non-turbo frequency. More adventurous options are, for example, to look at the RAPL MSR to read the current power consumption of the socket and infer from that what may or may not be available. In this way, we should also take into account the fact that the AVX workloads don't even reach nominal frequencies since they are very power hungry. Or again, we could keep track of the average frequency observed in the recent past and normalized against that. What I checked is... Yeah, sure. This is sure. You can know what happened in the recent past. Yeah, sure. But you don't know. Yes, this is. Yeah, but what happened in the recent past is not necessarily the maximum frequency a machine has.
Is that if you are running at the turbo frequency, then the number you get from the feedback register is greater than 1. And then you have to do something with it. So you kind of know that you are running at turbo frequency at that point.
Yes, you know, but you can go even higher and you don't know. Like, it's a possibility. I mean, turbo frequency, max turbo frequency you may have is 3900 hertz, 3900 megahertz, 3.9 gigahertz. Okay, this is a turbo, and maybe the fact that this is from a power envelope standpoint available to you now, like if you ask, you get it, it doesn't mean that you actually ask for it. So you might be going to some turbo state, but you would be allowed to go more, but you don't know.
I don't know.
So recent past does not tell you what is actually available. Like recent past is what happened. So again, I tried 1 and 2. Those 3 and 4 are more complicated. So let's start easy. That's what I.
Did you find any difference between 1 and 2?
2 is a tiny bit better than 1 in a few cases, but they are both a lot better than baseline.
Right. For 2, did you also think about just taking like 50 percentility to a point?
50%. I didn't.
Like the curve is like pretty steep, so as long as you go more than 4 cores but less than all cores.
Yeah.
Taking something in that.
Yeah, something in between. Yeah, sure. I did not test it, but sure. It's like let's get something less than the very maximum.
It's the max only gets like it's 1, 2, and 3, 4. Those boosts are really high. Desktops. It doesn't matter for cell.
Yeah, the all cores is not very exciting frequency. It's kind of low. Yeah.
So I will try 2-core turbo.
4, at least.
4-core.
2's too low.
2 is low, okay.
And the drop off at the front, that curve is like.
What would you try? Wait, the two.
So we have agreed on 4-core turbo.
For
4-core turbo.
okay,
It's an interesting point.
That's an interesting point.
but 4-core turbo is absolutely like whatever how many cores you have, just go for it.
Just like the 4-core point on the turbo curve.
Okay.
Maybe more interesting than
Okay.
the 2.
So we don't parameterize on how many cores are in the socket. Just go for 4.
4-core turbo as defined as the maximum frequency you can get on 4 cores at the same time.
Or maybe while you're running tests, you can actually try.
Yeah, well,
Yeah.
right?
No, but in fact, my patch I write on SysFS the max. So
Yeah.
so it's the same patch actually, but I just.
And then you just look and
He just runs it.
So Vincent Guittot, new pattern back. Sure.
The frequency turbo is also depend from the number of stalls that you are doing that moment. Because there is a register inside of the system, which is the performance bias register. You can move between 0 and 15. And this Intel doesn't explain how better this works. And from the startup of the system is just in the middle.
Okay.
It's like 6, 7. And if you move these, the turbo frequency vary between also the number of the stalls that you are doing at the moment.
Okay, that makes sense. I didn't know that.
Because so if you are not efficient from a code point of view, your turbo frequencies decrease.
Okay. Yeah, thanks. I didn't know that. So Vincent Guittot, new frequency. So Vincent changed the way frequency invariance is done in PELT. This patch has a long history. I think it was first sent in 2015, like about a long time ago, and so it was reviewed over time and changed not in the essence but in some other detail. What does this patch does? We achieve scaling variance by dilating time and not by scaling the PELT contribution. So as I had this. In this diagram, so I didn't want to explain PELT Vincent patch to this audience, so I wanted to go quick over this, but I can't find where in my notes I had to read. Okay, so if we aren't running at the maximum frequency, the time seen by run Q will slow down accordingly. In the diagram, this diagram here, which is from the comments in the code, consider the half capacity situation and note how the PELT segments number 3 and 4 are larger than the other, so these are larger seen from the wall clock point of view. Also observe that when the run queue is idle, the PELT clock is synchronized with the wall clock. In this diagram, this is represented by the time counter jumping from 4 to 7, and 11 to 14. This jump to the future, so to speak, has an interesting consequence, which I will not describe here, but if you are interested in more details, I encourage you to read the corresponding code and comments in the file kernel /sched/pelt.h, or the corresponding email threads archived in LKML, or ask Vincent Guittot, which is in the audience. So.
Yeah, also, didn't you do a presentation on this last year? Which should be still in the archives somewhere?
I don't think this was it. It was? You did a presentation? Because I was here.
Yeah,
Okay.
I did.
Okay.
Was this this event or something?
Yeah,
But
that's
I first remember at that time I've got this way to increase. It was a bit different. The way I still not have figured out how to handle this between not idle and how to recover this last idle.
We can schedule an update if you want. We can schedule an update. We have
Maybe.
space.
How much time I have left?
Let me check.
Half an hour.
Half an hour? Okay. So about querying for the frequency you were in the recent past. On x86, as I said, it's hard to know the maximum frequency, but at least the frequency seen in the recent past can be measured to some extent. Let me describe a few model-specific registers. A-perf is a counter spinning at the actual frequency of the core. A-perf, average performance. It stops incrementing when the core is idle. M-perf is a counter spinning at the maximum non-turbo frequency, which is a known constant value. So A-perf spinning at a variable speed, M-perf spins at constant speed, and they both stop at idle. The speed of M-perf is the maximum non-turbo frequency. And so note that when a core runs within the turbo range, A-perf increments faster than M-perf does. PSC or timestamp counter is exactly like M-perf, but does not stop at idle. So with these ingredients, we can compute three useful metrics. One is average megahertz, which is the can you read it? Average megahertz, which is the average frequency the core has been running at during some period of time. This value possibly includes idle periods when the core's frequency was 0, but we are averaging over the whole time. Busy percent is the percentage of time the core has not been idle during time interval, so the percentage of time was busy percentage. And busy megahertz is the average frequency in a time interval, but after removing all the idle time that has occurred. So this is just the busy megahertz. So this is what we can actually ask, as those metrics tells us what happened in the past. So this is Peter Zelstra patch with I removed the part where let's describe this patch, this diagram. So there is a global state with a variable which is 3%, and a constant that in my prototype I was setting from SysFS, which is the max frequency I wanted to normalize against. At the tick, we read A-perf and M-perf, do the subtraction with the last time we read them, so we get a delta. And our frag percent is busy megahertz divided by maximum frequency. Busy megahertz, we saw how to compute it. If obviously this can go larger than 1 because we might run faster than the maximum frequency I'm declaring in that constant there. So I could be running faster. That's the point of this. The only way this never get executed is if your max frequency is the 1 core turbo level, like the maximum possible. But if you declare something less than that, you might surpass it. So I clip at 1 and then I write it back to this first view variable. So this happens every tick, and when PELTs want to update, you, as we saw, we dilate time.
Can it be interesting to actually know how many times we have to set it into 1, like running in a long, while running a long use case? just to understand.
Yeah,
how much time
absolutely. Because this means that somehow we lost information.
Yeah, just to have an idea.
Yeah, that's true. That's true. Yeah.
I have a question. Reading the APF register is expensive.
Yes. Yeah, very much. Like I out of interest, I did the experiment on a few machines, and what I found was that, like on this laptop, which is very, I think it's Nehalem, but I guess this is a very old machine, is 500 clock cycles, but on a recent machine on my Skylake, it's 1,000. But 1,000, but the Skylake is much faster.
Yeah.
So it's kind of it's not the same latency on the laptop and on the Skylake, but sort of. But machine is slower, takes less cycles. Machine is faster, takes more cycles. Anyway, between 500 and 1,000 cycles, which means microsecond scale.
But are you reading this register from the kernel space?
Sure, kernel, yeah. So, and then we get we compute the PELT and we put it in, I mean, the PELT does its thing. You know? I think I exhausted the, so now it's the results. So these are the benchmark that didn't show any change. Then I will show you the benchmark that did show a change. So this is PG bench is IO. It comes packaged with PostgreSQL. And in this case, this is the read-write variant. I also use the read-only variant just to see that. But there are read-write use case and read-only use case. Flexible I/O, an I/O benchmark, no change. Computational intensive, those are HPC workloads from this NPB suite of benchmarks. We tried using MPI for message passing and OpenMP just to see if it makes a difference. So there's NPB, this benchmark set consists of several kernels. All the stuff you do, it tries to replicate the typical HPC workloads. So those kernels may be integer sorting, gradient descent, matrix multiplication, this kind of stuff. So I write some computational kernels are neutral, because some others are a bit less neutral, you would see. Like this is the non-neutral benchmark. Oh, this. So NAS, my hand is shaking a lot. Okay, so this is the NAS, each line is a different computational kernel. So they are here, but they don't change a lot. So let me first, so this is a very dense slide, obviously, and let me unpack how to read it. But there's a very non-obvious thing in this, in the user interface of this table, which is that the colors here do not tell you the magnitude of the change, but the statistical significance. This is something that we are used to in our team, but if you don't know it, you say, oh, this is more red, it's worse, but it's actually just 1%. But once you get used to it, it makes like you start to filter out the non-colored stuff because it's not significant. And you only, because we have in this, in our grid, we have hundreds of this, the table are large because we do more benchmark than that. We have around 300 benchmarks that we, in our collection. Test, which Dario mentioned yesterday, is a collection of benchmark that Mel Gorman, my manager, and other people collected over decades, I guess. And some are more reliable, some are less reliable, but we run all of them. So this is just a technique to read it, the table, because we have these huge tables and takes like, may takes like half a day to see if there's, so anyway. What, so this is the, so, and now I also, so, there are 3 machines here, my Skylake, the Broadwell, and the Haswell. Why don't I have the slide? Don't tell me that I forgot. this one. I skipped that for some reason, but this is my test boxes, okay? Skylake, Bradley, Haswell, kernel 5.0, file system is XFS. So these are my 3 machines, and for each machine you see 4 columns. First column, as I write here, is all core turbo without Vincent. Then 1 core turbo with Vincent. All core turbo with Vincent. 1 core yeah, it's not the best ordering I could think of. Now the thing is that this is now the order is stupid because it's the order in which I ran it, okay? And then I just copy pasted the table on this. It was hard to make this thing in LibreOffice. I mean, no, seriously. So the first thing I did was turbo all core, because that was Raphael's suggestion. You should try turbo all core, and I tried it. And then I remembered that Peters every time said that 1 core turbo works well with Vincent. So I said, wait a second, maybe Peter is right. Let me try that. And then I thought, wait, but maybe this Vincent thing can help also the all core. So let's add Vincent. And then I said, no, wait, maybe Vincent doesn't do anything, he just doesn't play against it. So that's the reason of the ordering, okay? So these are the benchmarks that change the most. And you see that when I saw this table, this is almost embarrassing. Like this Git source thing, it's not an industry standard benchmark, but we use it. It's running the Git unit test suite, and we do it because it's a bash script that runs for a long time, and so it's very bash intensive. And people in IT use bash for several things, like critical infrastructure and everything. So we want to know where we are, where do we stand with bash. So this is a shell intensive workload, which means fork a lot. So we want to see that. And you see that this thing is like half the time. See that? So when I saw this result, I said, what is happening? You know, I don't understand it. This doesn't happen every day. This is not a magnitude that you observe. We usually do 1%, 2%, that's a good day. So, yes, it's true. So let's look back. That's important to notice that when I say half the time, this is a summarization of our Git source result. Because we run Git source. No, Git source is a bad example. This is the exact one benchmark that we run only in one way, because it's very serialized. You just have this bash script that you don't have a way to scale it up. But tbench 91. This means 9% improvement because lower is better. We measure in milliseconds. So the less, the better. 9% improvement. What does it mean? It means that tbench, that we run it with 1, 2, 4, 8, 16, 64, 128 clients, because this machine has 80 cores. So this is parameterized, see what I mean? And then I do the geometric mean of those gains. Geometric mean because mean of a ratio is ratio of a mean. Doesn't hold for the arithmetic mean. You don't want to ask yourself, did I first do the ratio and then the average, or first the average then the ratio? So this is why the geometric mean, to summarize. So here you see a standard deviation which is very high. You will see that we are like 3% better with a 12% standard deviation. What's going on? Okay, this is the one case, because this bench, the tbench has a high variability. So this is why I also draw latency histogram. So let me show you the 4 client case. 18% improvement. Can I trust it when 18% is also the standard deviation? Yes, look at this. You see that? there is a this is the this is the baseline first, and then you have the 4 patches. That looks significant to me. You see? So the reason there is a high standard deviation is because the distribution is so fat, the tail is so long. But if you plot it, you see that this is significant. Okay? For the others, it's not the same. Like tbench is the same thing, but over the network. Just as tbench, so the same operations, but over the network. In the loopback, we don't use client server, but just one machine. But the operation is the same. tbench is backed by XFS, a file system. This one is over the network. The improvement here for all cores with Vincent, up to 66%. Standard deviation, 1%. So that's what I said, that the big boosts are in the lightly loaded. Actually, so if it's saturated, you don't even notice. But before, look at that. 66 peak of gain at 8 client. Well, 10% on 1, but 66 on 8. And then nothing at saturation. So this is the pattern that I noticed, is that the gains are in the middle. So this is the reason of the hypothesis of why this could be happening. I don't know, I didn't check. Those results are like last couple of weeks, because I noticed that Vincent patch was merged, so I had to rerun more tests because I wanted to include that, because I was thinking that would be interesting. So we are normalizing against the frequency that is in the turbo range. And this makes the core look artificially underutilized, because you're normalizing against something that's quite high. So the scheduler says, oh, you are underutilized, let's give you something more. And then, as a self-fulfilling prophecy, the core goes boost because we stuck things on a core. So this is why probably, I don't know, I have to check. But probably there is this phenomenon that you need, it was more evident on tbench. I mean, if you want to stack stuff, you need to get enough stuff. Because if you just have one, what do you stack? It's one task, it's one task. But if I have 4, I can compress all of them on a core, and this core go boost. So this is the why I think is a conjecture. I haven't verified it. I haven't traced it. Yeah. Okay. This is an interesting. This is an interesting. I don't know if I agree. It could be. It's easy to check. Just trace the governor. Traces. I mean, this is easy to verify. But what I don't know if you're considering is that the when we have the schedule chill non-invariant formula, which is this. The way we get this is by trying to approximate invariant util. So we sort of take that into, this is not frequency invariance formula. We try to do the normalization, even if it's too late, because we already got this out of PELT. Instead of normalizing every single contribution, we normalize the entire thing. So there is an effort there to have a non-dumb schedule chill when you're not invariant. So it's not like we are not utilization invariant, and so schedule chill is just a piece of junk. Oh, absolutely, yes. Sure, because you are feedback loop, he means that we have current frequency here, and we compute the next from that. The next is gonna be the current at some time.
Right.
then gonna be the next. So this is what Rafael is saying.
Periodically up and down, like in
Yes,
a regular pattern.
that's true. And so you, yes, I agree with you. That's true. So I don't say that the schedule chill non-invariant is the same as schedule chill invariant. They are different in the way that you are describing the feedback loop. That's true.
Yeah, so which may explain the difference because then you run slower.
Yeah, so you try, no, absolutely, because you try to follow the utilization, and what you do in the non-invariant case is try to keep the utilization at 80%.
And now if you happen to cross the turbo boundary with that, then you will get for a bit of time into the turbo range, then you
Yeah, you're right. I didn't consider that, but this is a very interesting mechanism that that makes the frequency selection in before and after the patch very, very different. Yes. So they could be, it's not like, as I was saying, that was causing a boost to happen, but just that I give it a better frequency.
Yeah, I was going to say, the schedule behavior isn't changing there. It's the governor's making a different prediction from it.
And do you have power usage, energy usage numbers?
I wanted to bring them, but I didn't. I collected data, but I didn't analyze it because I wanted to prepare a understandable presentation, and so that. But I can send it like next week. I had the data.
Because the performance per watt is of course also very interesting.
Yeah, absolutely.
Yeah, I was curious as well. Like when you have the 8 core, which is like boosted,
Yeah.
like the maximum performance with the it's this time the absolute numbers compared to the saturated case. Do you get like similar numbers, or so like is the 8 core performing as good as the saturated one?
I'm sorry, I was taking a note. I've asked to repeat the question.
My governor that runs the part from
Can you repeat? I'm sorry.
Yeah, no problem. Like sorry, I was saying just like in the 8 cores you get a good boosted number, and like comparing this absolute number with the saturated case, which is like when you run 128 for instance.
Yeah.
You get like the absolute numbers, like for instance the third column, the turbo all cores Vincent.
Turbo all core is this one. Yes.
So you get 66.4 boosted number,
Yes.
like performance. So if you compare this absolute number with the 128 for instance, you get like compared results. So is the boosted one is giving you better performance or comparable performance?
I know. I think that if you just want to go fast. No, I think that if you just want to go fast, there's nothing that is beating the saturated case.
At saturation your util's always max. So
Yeah.
So it doesn't matter. So the governor doesn't even have any choice.
the old behavior could be the same.
No, I think, I mean, when I have 8 active cores, 8 clients, I am doing better than before the patch, but also I cannot change anything because if I put a task in, so I don't know, I think.
Honestly,
That was my previous.
the frequency selection only matters for systems that are partially loaded. If you are idle all, then it is totally non-interesting.
Yeah.
If you are 100% loaded, it also is totally non-interesting. So
Yeah.
it is only interesting in the middle. And
Yeah, you're right. No, this is it. It's gonna be. It's the better frequency selection. That's it.
Right, and it's totally visible in your data actually that where the frequency selection actually matters.
Yeah,
Because
it matters here.
Right.
Yeah, that's it. We solved it. We cracked it. Yeah.
There is maybe another impact, is that from a load balance point of view. Before my patch, with the turbo 1 core, for example, your utilization will almost never be to the max value. So from a load balance point of view, your CPU has capacity, whereas with my patch, you can reach the max value.
Yeah, but NR
And
running
you will
dominates.
spread that a bit more on
But
CPU.
if you look
No,
at the figure show,
this is partial load. Well,
the
NR
figure
running
show
will
that
dominate that. It will just spread. It won't do anything.
So if you look at that and a difference between your patch and without, then there is no difference, basically. So I wouldn't think that this is
No, there'll be no change there because NR running will be all that matters.
Yeah, I finished. I have nothing else to say. Are we? What time am I?
No, we passed that, but because we are
Late.
Yeah, we're running late. You actually have 5 minutes more.
5 more minutes? Okay, so the goodbye slide, which is, oh, no, runtime search. I wanted to say this. So in Zelstra patch, Peer was defensive against a machine that doesn't tell you what the turbo frequency is. And so you were looking for it at runtime. And my question are, because that was that is, I wouldn't know how to do that for something that is not the max. I just take a fraction of it. Do I have to do it? Are there machines that don't tell you the turbo level?
I don't know. So the AMD machines.
There are. So they are mostly Atom SKUs.
But the atoms have a different MSR layout.
No. You need to derive that from very magic formulas. So don't do that.
So with the Atom, I should do the runtime series is necessary if you want to have this.
Yeah, so in Atom there are formulas for deriving the max turbo frequency, but they are
Proprietary.
specific,
No.
and you have to do it in different ways for different atoms.
But those formulas are available to the public. I can put it in the patch.
They are in the Intel state driver. You can just
Okay.
and then take them from there.
So no runtime search needed in Atom.
No.
Okay.
In principle,
Oh.
if you want to have that code somewhere in the x86 startup code instead of Intel state, because it's not we code.
And you'd have to look at the AMD systems. I have no idea what.
Okay.
Also, yeah.
Because they have a turbo thing. I'm pretty sure they do. Yeah.
They have curves much better. They don't have the peak for 1 and 2 core.
Okay. Yeah. So I mean, we covered all the. So if there is no other remark or question, yeah.
My only remark would be, so it's not possible in your case because accessing this APEF is quite slow, but otherwise that would be interesting instead of scaling the time, just to use this hardware clock counter as a new clock.
Yeah. You can't do it very frequently.
Yeah, I haven't get time to try that on a ARM platform, but that will just simplify it.
You have a similar counter in ARM?
Yes.
Some, yes.
Ah.
Yes, they're called activity monitors.
Ah.
They are present in A75 and A76, but only on some of the platforms that implemented, so it's an optional feature. And it will be available on, definitely on 8.4. So, yeah, at the moment we can only experiment with those in models.
Sure, I understand. Yeah, they have high latency, so it cannot be queried very frequently. So, yeah, if we're good, I think we can. Okay, thank you very much.